Okay, yeah, let's start. Okay, are you?
Go ahead. Yep.
Is recording now?
Mhm.
Okay, so today we are very pleased to have Dr. Yuesheng Xu to give our 1W-MINDS seminar. Today, Dr. Yuesheng Xu is currently Professor of Data Science and Mathematics at Old Dominion University. He received his PhD from Old Dominion University in 1989. He has held several distinguished academic positions, including Ably Chair Professor of Mathematics at West Virginia University, Professor of Mathematics at Syracuse University from 2003 to 2013, and the Guo Hua Chair Professor of Mathematics at Sun Yat-sen University from 2009 to 2017. His research has supported by NSF, NASA, DOD, and NIH, and his research interests include numerical analysis, applied harmonic analysis, image and signal processing, medical image, and machine learning. His notable contributions to mathematics and machine learning including developing multi-scale methods for solving free-whole integral equation, established the universal kernel theory, and including the concepts of reproducing kernel Banach space. He has served as an editor or associate editor for different mathematical journals, including as managing editor of Advanced in Computational Mathematics. Today, he will talk about multi-grade deep learning. Dr. Xu, your turn.
Okay, thank you. Thank you, Longshu. Thank you very much for the invitation and the nice introduction. Yeah, okay, I'm going to talk about multi-grade deep learning, the project that I'm currently developing. Okay. Okay, so this is the table of contents that I'm going to talk about today. So I will briefly introduce the concept of deep learning and to discuss the challenge of the traditional deep learning training, and then to introduce the multi-grade deep learning model, and to show a couple numerical experiments to compare the performance of traditional deep learning and the multi-grade deep learning. Okay, so all of a sudden, we are in the AI, time, and everybody talk about AI now. It become a very hot topic, whether we fully understand or not. But from the mathematical point of view, at the cause of AI is machine learning or deep learning. And we know machine learning involves models and algorithms, okay, that can analyze data, learn patterns, and apply technology to make intelligent decisions. And AI relied on the decision functions to make the intelligence decision. Okay, so the effectiveness of learning model largely depends on the expressiveness of the decision function. Okay, so the decision function is the one from the mathematical point of view, the one is important. Okay, and traditionally there are many class of functions used in machine learning. For example, polynomials, trigonometry polynomials, splines, finite elements, weblet, framelet, kernels, and also shallow neural network. This has been used, before the 2010. Okay, and then after probably 2010, the deep neural network become very, very hard. Okay. But the traditional method is, we construct a decision function using linear combinations of pre-selected basis function. So this is the illustration of the linear combination. Okay, suppose we have we given data, we want to construct this curve. Okay, we use here is like a cubic spline, use the linear combination of cubic spline to represent this. Okay, but there is another way to represent function, using function iteration or function compositions. Okay, so, for example, the Big Bang is a nonlinear process, which is characterized by severe singularities. And this kind of function is they're difficult to be represented by linear combination of pre-selected basis function. Also, mutation or evolution, also nonlinear process, and the function composition serve as a more effective mathematical tool for modeling mutation and evolution. Okay, I like this image. This is iterate function systems. For those who working on wavelet or fractal, probably knows this very well. So the function iteration function systems, it's very good to model the nonlinear process. Okay, now the deep neural network, in fact, is a hybrid of the traditional linear combination and the function iteration function systems. So deep neural network employ functional composition in hidden layers and linear combination of features, or we can call it an adaptive basis function in the output layers. Now, why deep learning? Okay, in fact, deep learning scales significantly better with increasing amount of data compared to other models. So, the traditional model maybe work well with, when the amount of data is small. But once we have more data, the traditional model reach its limits. But the deep neural network, deep learning, can significantly outperform the traditional model. So deep learning leverage deep neural network with multiple layers to represent decision functions. And deep learning can be supervised, semi-supervised, or unsupervised. And then in terms of the network architecture, that deep learning include many different type of network. For example, the total connected network, convolution network, transfers, and deep learning excels at recognizing complex patterns, making it highly effective in tasks such as imaging recognition, natural language processing, and predictive modeling. The mathematical foundation of deep learning lies in deep neural networks. Okay, this is an illustration of a deep neural network. This network has 3 hidden layers. So we have the input layer, and then 3 hidden layer, and this is the output layer. This is a totally connected network. Okay, so mathematically is we have the input space and then output space. Input space could be the Euclidean space of dimension d0, and then the output space could be the Euclidean space of dimension d sub capital D. All right, and then we have the weight matrix and bias, and then we define this affine map. This is the x sub I minus 1 is the input in the ith layer. Okay, and then you have this affine map. And after we have the affine map, we use activation function, a sigma I at the ith level. You know, the activation function could be the same or could be different for different layer. And then the output of the ith layer is x sub I defined by applying the activation sigma I to the affine map. All right, and then the output layer is xd. You know, just we only apply the affine map L sub d to this the input. Okay, and then you can the DNN can be written in this form. You know, the composition of affine map with the activation function often is a nonlinear function. Okay, and then we correct all the parameters together. We call this theta. Theta is defined by this the matrix Wi and the bias vector Bi. And this is called trainable parameters. Okay, so now it gives you the idea of the example of a training model. This is an optimization model given input vector, the data, and then this is y sub I is like a label. You know, this is also a vector. So we have a loss function L, okay, and the L can be in different form, and you know, one of the commonly used is the L2 norm of this vector. Okay, so we define this training model, and so this is the model, and then we use some kind of optimization method to solve this optimization problem to find the optimal parameter theta star. So once we get the theta star, we get this vector. This is a vector value function. Okay, and this is a function. So once we have a new input x, we evaluate this function, and the function value serve as a prediction of the labels. Okay, now the challenge of traditional deep learning is because we are training a highly nonconvex optimization problem. We're solving a nonconvex optimization problem. Okay, and this could cause a lot of problem. It's, you know, one issue is because nonconvex so the optimization, highly nonconvex optimization often start at local minima. And also because the neural network the neural network is very deep, you have many layers. Okay, so you know, when you use gradient descent method, type of gradient descent methods, we have to compute the gradient, and the gradient use the chain rule is the product of the gradient of each layers. And this could cause the gradient managing or gradient exploiting issues. All right. So, and then there's another issue been identified. You know, one of the major problem is the spatial bias. The DNN exhibit the spatial bias. So there is the tendency to prioritize learning low frequency components of a function and take a long time to get to the high frequency. It is able to in the training process. So let me show you an example for this about this spatial bias. Okay, so this is the signal in the bool is the function we want the function we want to construct, we want to approximate, and you know, this is the single grid, the traditional deep learning methods to learn. Okay, and the first 1,000 iterate step, you only learn this little bit, and then 10,000 learn this one, and then 20,000 improve, and then the 30,000 step get this, but still have some there's some stuff missing. Okay, so this is show us the spatial bias of traditional deep neural network. Okay, so I have been thinking to improve the learning model of the DNA model, and then so the idea of the multi-grid deep learning is motivated from our human education. So our education typically structured into 5 stages. We have elementary school, middle school, high school, college, and graduate school. And each stage also divided into grades. So for example, elementary school consisted of 5 different grades, right? And then the curriculums is designed progressively by grades, okay, incorporating substantial redundancy and advancing from basic concept to deeper understanding, from simple to complex topics. Okay, and then the knowledge acquired in one grade serve as a foundation for learning new concepts in the next grades. Okay, and at the end of each grade, students undergo an evaluation to assess their understanding process. So the learning, human learning experience demonstrates that the multi-grade learning model is both effective and efficient. Okay, so motivated by this, I propose the multi-grade deep learning. Okay, and so instead of optimizing the loss function end-to-end, we solve a sequence of smaller optimization problem, each focus on learning a shallow neural network with only a few hidden layers. So this optimization problem are structured in grades, where each grade extract information from the residuals left by the previous grade. At each grade, a neural network with a few layers is trained, while being composed with the neural network learned in previous grades. Okay, those learned in previous grade has the parameters fixed. Okay, the parameters will not be updated in the current grade. Okay, so this significantly reduces the complexity of the optimization problem. Each successive grade builds upon and refine the learning from the previous grades and gradually enhance the learning outcome. And the original idea was is in my paper was post in the end of I think end of January of 2023, and there is another paper. It's called successive affine learning for deep neural network. Is in the middle of the years. Okay, in fact, I had this idea for a long time, and I didn't have the chance to write it down until we all get locked out by the pandemic. So I spent some time to write it down at home. Okay, and I written these 2 papers, and now both there was some struggling, and now both are now accepted. The first one has been appear, and the second one is being accepted by analysis and application. Okay, so here there is a description of the mathematics of the model. Okay, now we consider we're going to train a deep neural network of D layers. Okay, and now we decompose the D into L positive integers. Okay, so each one K sub L is a positive integer. All right, and then we are going to learn L optimization problem. Okay, and each to construct a DNN with K sub L layers. So now learning of grade 1 is okay. It's the same as the usual learning, except K1 is small, small number. Sometimes, from our experience, K1 could be 1, 2, or 3. Shallow network. All right, and then so once we learn, so we learn this solve the same problem, except this is shallow neural network. Okay, so we find theta sub 1. This is the parameters. Okay, get the optimal parameters. So once we get this, we remove the output layers. Okay, and so we call the inner network actually, we use the actually to denote the inner network. All right, and then we build upon the inner network a new network. Again, this is the network with a very few number of layers. Okay, and the parameter of the one we learn, we just start. That means the parameters are fixed. So the only parameter we are going to learn in grade 2 is this WJ2 BJ2. All right, and now we solve in grade 2. We solve this problem. All right, so this is like to learn from the residual. All right, and then once we learn we solve the parameter theta 2 star. Okay, we construct this function U2 star. Okay, and then the approximate solution come out from grade 2 would be U1 star plus U2 star. All right, and then again, to continue this process, we remove the output layer, and then we compose the new neural network. Okay, so the previous network learned from the previous grades, is a dose network, and then we're going to learn the parameters in here. All right. So this is the idea of the multi-grade deep learning, and this in the grade L we solve this problem, and the both learn from the previous one has to be here, so that we learn from the residual. So once we get the parameters, we get the final outcome is this U L bar star. That is the summation of the network that we learn in L grades. Okay, and we continue this process. Okay, so this can be illustrated by this figure. Okay, here we have the input. We have 3 variable. Output is 1 variable, and here we have the 2 hidden layers. So this is the grade 1. So after we get the result, the parameter of grade 1, we remove the output layer, and then we compose with 3 more hidden layer here on the top of the one we learned. Okay, and then the grade 2 is to learn the new parameters here. Okay, so let me show you compare the multi-grade deep learning with the single-grade deep learning, the performance for this example. All right, so we use the same network structure, except this is learned by multi-grade. Okay, so grade 1 learn a little bit. It's better than the 1,000 iteration of the single grade model, although it's a shallow network. And then grade 2, this is the outcome of grade 2. Is better than this one, and then the grade 3, it's already better than all these 4, and then the grade 4, gives you the perfect outcome. Okay, so in terms of training time, the single grade, in this example, the single grade use 32,000 seconds, and then the multi-grade use less, the less computing time, only 27,000 seconds. Okay, so here I want to illustrate to you why multi-grade can perform better. Okay, so suppose we have a function with high frequency. Okay, this is in the Fourier domain of f. Okay, so the f hat is the Fourier domain. Okay, helps the frequency around 200 is still significant. Okay, this function can be decomposed in this form as f1 plus f2 composed with f1 plus f3 composed with f2 composed with f1, and then plus f4 composed with f3, f2, f1. Okay, it can be decomposed in this way. And each of these 4 functions, f1, f2, f3, f4, they all has the low frequency. So you look at the frequency is concentrate of these 4 functions, concentrates this from 0 to 75. Greater than 75, this is insignificant, it's very small. Okay, but the composition of the composition of this function and then the combination of them can be used to represent a function f that has a significant high frequency. Okay, and so this example also motivates us to construct this multi-grade deep learning. So shallow network can effectively capture the low frequency function, right? Now, composition low frequency function can naturally generate a high frequency behavior. Okay, if you compose a couple of low frequency functions together, right, you can use to represent a high frequency. For example, you compose cosine 2x with cosine 3x, they can use to represent the high frequency. Okay, so and the high frequency function can be well approximated through composition of low frequency function, right? Okay, now the composition of shallow network provide an efficient representation for high frequency function. All right. Okay, so the shallow network corresponding to low frequency, right? And then the composition of shallow network corresponding to composition of low frequency function, but that can be used to represent high frequency functions. So that is the idea. Okay, so training a sequence of shallow network significantly reduce the computational complexity compared to training a deep neural network. Okay, so this is the fundamental mathematical principle of MGDL is we can use composition of shallow network to model functions with high frequency components. Okay, and now this is some theoretical justification for the multi-grid deep learning. We can establish the this error, this loss function. If the grid is bigger, this is the loss is smaller, and if the contribution from grid L is non-trivial, then we can prove this is strictly smaller than the previous one. Okay, and also this process either terminate at the finite grids or the optimal error sequence, is strictly decreasing. Okay, and then so that is about the accuracy. Now we can also talk about the convergence of the training, because the multi-grid deep learning, each grid only solve optimization problem for the shallow network, right? So this can mitigate the gradient managing and exporting issues, okay, commonly encountered in deep neural network training. Okay, also we can apply gradient descent. This is simple methods, gradient descent methods applied to this optimization problem. Okay, and with the convergence guarantee in certain sense. All right, and computational complexity of the multi-grid deep learning training scales linearly with the number of grids. Okay. Of course, we have to assume each grid has the same number of layers. Okay, and then it's not difficult to prove. This is a linear. The computational complexity increase linearly. And now multi-grid deep learning is interpretable learning model. Okay, in contrast to the standard deep learning model, which often function as a black box. It's difficult to tell what's going on. Okay, so let me show you some numerical result. So here is a signal representation example, which you for different cases. So the first one is we have the constants frequency. The frequency is constant, and then there's a decreasing frequency, there's a varying frequency, and then there's an increasing. It turns out the increasing one is the most difficult to learn. Okay. And we use this a single grid deep learning is a hidden layer, and each layer has 256 neurons. And then we restructure into 4 grids. Four grids, okay. And the 4 grids, yeah. And then for the increasing frequency, we because it's difficult to learn, so we use 2 more grids, okay, 2 more layers, okay. So we add grid 5 to it, and the activation function for this case is ReLU. Okay, and here is the result. Okay, for the numerical result, this is the accuracy. for the test data. So the multi-grid deep learning for the constant case is 4 orders higher than the single grid deep learning. And the decreasing case is about 3 orders higher. Okay, the varying one is 4 orders higher, and then the increasing one is 2. It's 2.5 probably, yeah. So you can see, this is the loss of the single grid deep learning, and this is the loss of the multi-grid deep learning. And for the last case, we have 5 grids. Okay, and this structure, the single grid, this one is also have the same network, same number of the layers. So this show the deep learning, the multi-grid deep learning significantly improves the result. Okay, and then so let me just show you the most typical one, this increasing frequency one. Okay, okay, this is the true signal, and this is the signal learned by multi-grid deep learning. This is the signal learned by single grid. The single grid, it's difficult to get those, those frequencies. Okay, this figure shows how grade 1, grade 2, up to grade 5, how this what is it learned, So the grade 1 learn some low frequency, nothing in the high frequency. You see, grade 2 learn the middle. This is the yellow one, right? Learn the middle frequency, and then grade 3. This is the green one, the middle and the higher one. And then grade 4, basically the relative higher one. And then the grade 5 learn the higher frequency. Okay, and now let me show you some other example, the imaging representation example. So we compare multi-grid deep learning with single grid deep learning, yeah, to the 2-dimensional color imaging. Okay, the color imaging is the output function is a vector. We use the RGB model, RGB values. Okay, so it's a vector of dimension 3, right? All right, and then we use 12 hidden layer. Okay, so the input is the 2-dimension, output is 3-dimension. And then the multi-grid, we use 4 grids. And each grid have 3 hidden layers. Okay. Okay, now this is the WRF imaging. This is the paper published recently in NIPS last year conference, NIP conference. In our paper, I call this CAT, but in fact, one of my students indicated this is not CAT, this is WRF, so I changed to WRF imaging. You see, okay, grade 1 learn the low frequency, right? Grade 2 learn low frequency plus some details, okay? And grade 3 is more details. Grade 4, this is the PSNR value of grade 4. Grade 4, we got 24.14. And this is the one learned by single grid model, which is this is the optimal result, the best result we can do. We can learn this to give us 22.84, and it is one true. And you can see, this this is a loss, the PSNL loss value. Okay, the multi-grid shows some overfitting, significant overfitting in the grade 3 and grade 4. But the single grid is less, is not obvious. Okay, and we analyze this. We believe if we let the single grid continue to run, it will eventually shows the overfitting. Okay, but because the multi-grid learn quick, right? Okay, so so the shows the overfitting, it shows sooner. Okay, the obvious overfitting sooner. But nevertheless, there's the quality improve, by about 1.5 dB. Okay, this is the C imaging, and this one improve even more significant. It's 4 point something dB. Okay, so this is single grid model. The PSNR value is 20.0, and the multi-grid, the grade 4, we get 24.34. Okay, and again there's some overfitting, and this is the issue we need to address in the future research. Okay, now this is the building imaging. Okay, and grade 1, grade 2, you see grade 4. Yeah, the PSNR value is 22.05, and for the single grade is 19.52. All right. So, and then we also consider other application of multi-grid deep learning. I work with my former students, and this is to solve oscillatory Fredholm integral equation. This paper has been published. And then there's another piece of work is to apply these methods to solving PDE with my former students. And this paper is still under review. Okay, so let me summarize. So the multi-grade deep learning enable grade-by-grade learning, where each grade requires solving an optimization problem for a shallow neural network with a few number of layers. Networks learned in previous grades serve as adaptive basis function, or we can call it features, for the current grade, which learn from the residue of the previous grade. Each grade solves an optimization problem for a shallow network with guaranteed convergence in certain sense. The error at each grade decreases monotonously, while computational complexity grows linearly with the grade number. And the multi-grade deep learning provides interpretable learning framework of learning model as opposed to a black box model. Multi-grade deep learning supports adaptive learning because you don't need to, if you're not satisfied with the network, you don't need to learn from beginning. We just add more layer, add more grade to it. Okay, so this serves as a foundation for adaptive numerical solution of operator equations, including integral equation, ODE, and PDE. Okay, I would like to end my talk with this quotation. The grade doesn't happen through impulse alone, okay? And it's a succession of little things that are brought together. Okay, this is due by Wenger. And then I like this one, less is more. And Lao Tzu, the Chinese, ancient Chinese philosopher, he say, a journey of 1,000 miles begins with a single step. And deep learning with 1,000 layers Okay, begin with training a shallow network. Thank you very much.
Thank you very much for the excellent talk. Let's thank our speaker. If you have any questions, feel free to unmute yourself.